So, in your podcast homework last night or previously, we've covered how to predict the products of combustion reactions, which are always the same two products, also of synthesis and decomposition reactions, where we're either just breaking all of the elements apart or putting them all together into an ionic compound. Now we're going to touch on how to predict the products of single replacement and double replacement reactions at the bottom of page 10 and the top of page 11. So starting with these single replacement reactions, there's actually two different types that are written out here and that we're going to focus on separately. And this first type is the type where we have a metal as our single element. And so if we have a metal as one of our single elements, then it might replace the first element that is there in that compound. And this is because metals like to have positive charges. And so they're going to replace the positively charged part of the compound. Because every compound has to have a positive and a negative piece, we have to pay attention to what charge that single element is going to have when we're coming over and trying to replace part of that compound. So, notice though that I said may replace that first element in the compound. It's not necessarily always going to happen. And the reason why is because of this activity series arrow thing that you see over here on the right side of your page. Remember that we called these single replacement reactions the homewrecker reactions because we got this single element that doesn't want to be single anymore. It's coming over to this nice, stable, happy compound and trying to break it up and become part of that compound and kick someone out of the compound so that they're single instead of whoever started off single. So, not necessarily the happiest analogy, but it helps you really understand how these elements are moving and changing. And if we continue that analogy just a little bit further, if that compound was super stable and super happy together, then that element that's trying to break it up might not actually be super successful. If you've been in a relationship for years and years with the love of your life, and some random person walks in off the street and is like, hey, why don't you break up with your boyfriend and be with me instead? You're not necessarily going to do that. Not if they're not going to help you be more stable or more happy than the relationship and the compound you've already gotten. So the elements all agree on who the best metals to be with are. That's what this activity series is. Lithium is going to form the strongest bonds, the most stable compounds. So every single element wants to be with lithium. When we talked about this in class, students were saying that lithium was kind of the Zendaya of all of the elements on the periodic table. Just the hottest one out there, most desirable, most stable. Everyone wants to be with them. And just the best, coolest element out there is lithium. So lithium's at the top of every single element's list on who they want to be with. If lithium walks into the room, then any element is going to break up with the other elements that it's already with in order to try and get with lithium. As we go down the list, then these elements are a little bit less reactive, a little bit less stable, and not able to necessarily break up another more stable element in its compound. So let's clean this up real quick. So when we look at a single replacement reaction, the important thing, like we just said, is figure out who that single element is trying to replace in the compound. So like we said, our metal, magnesium, is going to be trying to replace the first element in this compound, iron. What we need to do is go and look at magnesium and iron on the activity series. And this is going to tell us who that nitrate ion would rather be with. Whoever's higher up on the list is who they want to be with. And since magnesium is higher up on that list, nitrate wants to be with magnesium. Magnesium's going to get the girl. And because magnesium's not already with nitrate, then we're going to actually have that replacement reaction happen. Magnesium and nitrate are going to get together. If we take a moment to check our charges, magnesium is a +2 and nitrate is a -1. So when we cross-drop reduce that, the 2 is coming over onto the nitrate, and the 1 is, well, would be coming over onto that magnesium, but we don't have to write those, so we're not going to. So I need to put parentheses around that nitrate before I put that 2 there. And then because magnesium is now with the nitrate, then our iron is single and is going to be written out separately from our compound. So this is this classic single replacement reaction where we start with someone single, and then we end up with someone else single after that reaction. So just moving those pieces around, you just need to make sure to check the charges of your elements when you put them together into this new compound here. Don't let it throw you off that we only have 2 nitrates here instead of 3. Remember, most reactions don't start off balanced. You always have to check the charges of the pieces that you're putting together. And once again, kind of thinking of this like relationships, even though nitrate is still part of this compound, still part of that relationship, it's a slightly different relationship that it has with magnesium than it did with iron. And you don't always have the exact same relationship, even though you're in part of it. That relationship dynamic changes a little bit. The ratio of those elements have to change in order to be perfectly stable and neutral. So remember, anytime you put atoms together, we're not going to be bringing those extra little subscripts with them. Of course, nitrate is always going to be that NO3 group. That 3 on the O comes with it because that's part of nitrate. But because that other 3 wasn't, we don't bring that with us when we come to the other side. And we just have to check the charges of those 2 pieces that we put together and cross-drop reduce them if they're not equal and opposite already. So if that bothers you, you can always balance these reactions. I'm not going to be focusing on balancing them here. I just want to help you make sure you can find these products because we've been balancing equations like this before. But if it does bug you to see these unbalanced like this 2 and 3, in order to be equal, would have to both get turned into 6. So I'd put a 2 in front of the group that has 3 of them and 3 in front of the nitrates that are just 2. And then I'd have to fill in this 3 and this 2 there to get my magnesiums and irons equal as well. So now it's not only predicted the products, but it's also balanced as well. Now, when we look at our next example, copper is going to be trying to replace our zinc atom. And if we look at our activity series, then here is our copper and here is our zinc. And remember that the higher up element is the element that our chlorine would rather be with, or any element would rather be with. And because zinc is higher up, and chlorine is already with zinc, chlorine wants to stay with zinc. It doesn't want to trade for copper. I mean, who really wants to be with copper? So this is not going to react. Copper is not going to be able to replace that zinc. And so we can't leave it blank. What we write instead is no reaction. Let me make that look a little more like an N. In the future, I am going to let you abbreviate this NR, but for right here, I would appreciate it if you write no reaction so that future you understands and remembers what we mean by NR. So elements only ever want to trade up. They don't want to trade down. They want to be in a more stable, more happy relationship or compound, not in one that is less stable. So that's the only kind of twist to these reactions, but it honestly makes things simpler. You don't have to finish predicting any products or balance anything because nothing's going to be changing here. If I put a chunk of copper into a solution of zinc chloride, it's just going to sit there. You're not going to see any color changes or any other signs of a chemical reaction. So looking at this next example, magnesium is going to be trying to replace hydrogen. And let's see, magnesium, hydrogen. Magnesium is higher up, so magnesium is going to get to be with chlorine. When we put those together, magnesium does have a +2 charge, just like it did up above when we worked with it. So we are still going to have to bring a little 2 over onto that chlorine. And then because hydrogen is separate, it's coming off, it's going to be the single element now. But you need to be careful because this is a diatomic. So this has to be H2 here, not just H. If you were wondering why hydrogen is written in parentheses here, it's because technically it's not a metal like every other element in this list. It's a non-metal, of course, but it does have that positive charge. So it's going to replace and be replaced by other metals instead of non-metals. So that's why it's in parentheses there. So now it's your turn. I'm going to have you try out these next couple of reactions. 3, 4, and 5. Oh, sorry, 4, 5, and 6. My bad. I don't have my numbers included on here. Remember to start by figuring out which elements want to replace, which elements in the compound that single element wants to replace. That copper, or that first single element, is always going to be the one trying to replace another element in that compound. Look at them on the activity series. Remember that your elements always want to trade up. They're never going to trade down. If it looks like they're trying to trade down, then there's going to be no reaction. If they do manage to trade up, make sure you're checking the charges of those pieces that we're putting together in order to get them to be a nice, stable, happy compound. So you will have at least one here that is no reaction. So keep an eye out for that and come check in with me if you have any questions. But I'm leaving these for you to do, just like I did in class. So come check in with me if you're not confident in your answers or you just want a little bit of help figuring that out. And now we're ready to move on to page, we're ready to move on to our next type of single replacement reactions. There's still single replacement reactions, but in these, we don't have metals as our single element. We have halogens. Now, there are some other non-metals that we can use in single replacement reactions, but predicting those products start to get a little bit weird. There are some little side reactions that can happen. So at this level of chemistry, we're just going to have you work with metals replacing metals and halogens replacing halogens. The reason why these are kind of its own separate type, and I wanted to talk about them separately, is because there aren't any of these halogens in this activity series. You don't necessarily have to write down this blue stuff. I just want to point it out. There's only one non-metal on that activity series, and we just pointed it out. It's hydrogen. So the activity series doesn't help us as much here, but we still do need to be able to compare the reactivity of these elements. It just means that we have to flip back over and look at the periodic table to be able to see these halogens in their own groups. But if you remember back in Unit 3, we talked about reactivity of our metals and our non-metals. And so even though it gets a lot more complicated for our metals, our non-metals is a much smaller group and they're simpler. And hopefully what you might remember is that the most reactive non-metal element is fluorine, which happens to be a halogen. So if you look at that periodic table, fluorine is at the top of its group, and since it's the most reactive non-metal, that halogen group, that column with F, Cl, Br, I, and At, is kind of like its own little mini activity series. Fluorine is the most active, the most reactive, and so it's at the top. So I would recommend that here in your notes, you write down those elements in this order on that other side of that activity series so that you can see it and use it as we're doing these problems. But just remember, and I'll try my best to remind you before we test, that if you do see a halogen in a single replacement reaction, that you have to check the activity series or just the column of halogens on the periodic table. Fluorine is the most reactive, the most desirable halogen in that group. So the rest of the process is the same. Since I have fluorine here who's single, they're going to be trying to replace the other halogen in this compound, which is no longer the first element in that compound. Fluorine trying to replace chlorine will work because fluorine is higher up. So we're going to put Na and F together, and Cl is going to become single. Now, basically all of these halogens are diatomics except for astatine, although honestly, astatine is so unstable and rare to see in chemical reactions that you probably won't see it at all. So our chlorine comes off and becomes a pair, and when we put that sodium and that fluorine together, the great thing is that the charge of fluorine, as well as the rest of those halogens, is a -1. So just the formula that we start with that other halogen in it, is going to be the exact same formula that we end up with. It's just a straight swap, just switching out the F and the Cl, and their original compound formulas, the numbers and stuff would all stay the same. I'll actually show you another example that makes that a little bit clearer, perhaps, than these two. In this next example, bromine is trying to replace fluorine, but since fluorine is higher up than bromine, potassium, that K, would rather be with fluorine. And since it's already with fluorine, then this is going to be no reaction, or NR if you would prefer. Now, this is the example that I wanted to show you, just so that it's not like all super duper simple looking formulas. They can be simple, but we can also have something like aluminum chloride and fluorine mixing together. We're still going to compare and find, okay, this is fluorine, it's a halogen, it's going to try and replace the chlorine, and it is going to succeed at replacing that chlorine because fluorine is higher up. And so when we put that aluminum and that fluorine together, this is going to be AlF3 because I do still have a +3 charge on my aluminum, just like I did over there when it was with chlorine. And fluorine is a -1, just like chlorine was. So this becomes AlF3, just like this was AlCl3. And then our chlorine becomes single, but because it's a diatomic, just like fluorine was, it gets a 2 on it. So you can see this kind of symmetry between the two sides of our reaction here. And that's always going to happen when we have halogens replacing other halogens because they're all in the same column, so they have the same charge. It's really just basically switching those symbols around. So that's basically it for our single replacement reactions. Let's go ahead and look at our double replacement reactions. Now, these reactions are always going to happen. So that is an important thing to write down there. And the reason for that, if you kind of, maybe some color will help us see this. If you think about this as our kind of wife swap situation, where we have a buddy, a couple, and another buddy, another couple. And in terms of that old TV show, Wife Swap, they've just pulled the wife out of either couple and switched them, for shenanigans and ratings and stuff. So everyone started with a buddy, a couple, and everyone ended up with a buddy or a couple. The only difference is that the buddies swapped. And so no matter who you're starting with or who you're ending with, because everyone's ending up with a buddy, then someone is always trading up while the other is trading down. If you consider X to be the better partner than Y, and that's just arbitrary, if X is better off, a better partner, then that means that during the process of this reaction, B is ending up happier with a better partner because B is trading up from Y to get with X. But A is still ending up with Y. And so there's always going to be a more favorable reaction or kind of change here. And that's what's driving this whole process. B wants to be with X so badly that it's pulling it off of that A and making this reaction happen. And A and Y are still attracted because they're opposite charges, so they're just going to end up together because it's better than being alone. It's more stable that way than the other. So that's kind of some of the chemistry behind it. Someone is always looking to be more stable, and in double replacement reaction, someone always can get more stable. So these reactions will always happen. You don't have to check that activity series. Like I was talking about, charges are important to remember here. Every single compound that we're going to be asking you to write is an ionic compound formula, which means that they are all going to start with a positive ion and end with a negative ion. I know it's been a while since we learned our rules for writing formulas, but that was one of the first rules we talked about. Positive first, then negative. So when these are switching and swapping partners, we're going to have to always figure out where to break up our compounds and then how to switch them, swap them, to put them back together after the fact. And we're always going to end up with one positive piece and one negative piece together after the reaction. It's just not going to be the same positive and negative piece that they started with. So I really like using this generic formula, the A's and X's, to help you see this movement. As a positive piece from my first compound is going to get with Y after the reaction, which is the negative piece from my second compound. And then our B, which was the positive piece from my second compound, is going to be getting with X, the negative piece from my first compound. But even though when we're reading through this, we see X before B, we still put them together in the order BX because the positive piece always has to come first in our compounds. Always, always, always. That's the rule. So we need one of each piece, and they have to go in that specific order. So we're always going to be kind of following this pattern. It doesn't actually matter what order we write these formulas in. I could just as easily make that BX plus a Y, but it's still going to be a positive piece and a negative piece from each of those reactants. So this is our general process. When we see a double replacement reaction, we need to split up our compounds that we're starting with into two pieces. It's always going to be two pieces, and then take one piece from each and put them back together, making sure we get a positive and a negative in that order. So I'm going to leave those kind of color-coded things there, but we'll get rid of this purple stuff. There. And let's start trying this first example. So AgNO3 is a little bit harder to split up than just NaCl would be. NaCl is going to split up between the Na and the Cl part. It's just two atoms. It's simpler. So if you do have something that has three different elements in it, then you're going to have to think a little bit harder. But the truth is, it shouldn't be that hard, especially if you recognize your polyatomics from the back of your periodic table, because those special groups from the back of our periodic table are never going to get broken up. They react and move around as a group. So if you look at the back of your periodic table, NO3 is one of those special groups. It's nitrate. So when I'm deciding where to break up my AgNO3, it's going to be between the Ag and the N. So now I've got my two pieces, and I'm going to go ahead and take this positive piece from my first compound, the Ag, if I can highlight it here, there we go, and put it with the second piece from my second compound. And when I do that, I need to check their charges. Ag and Cl getting together, and Ag is one of those rare transition metals that does have a set charge. It's always a +1, and because chlorine is a -1, those cancel each other out, and so AgCl is our formula there. And then I have to take those remaining leftover pieces, the NO3 and the Na, and put them together. But I need to be careful to make sure that the Na stays at the beginning of the formula that we write out here. It's the positive piece. It wants to go first. It's kind of like being a line leader in kindergarten. Once you're first once, you're going to be the line leader the rest of the day. You just got to. That's your right. You always want to be first from then on out. So then we can put that with the nitrate. Still need to check those charges. Na in the first column is a +1. Remember that nitrate on the back has that just minus sign. That's not a -3. It's just a minus charge, which means it's a -1. So once again, +1 and -1 cancel each other out, and we don't need to add any more numbers to make these a nice, stable, happy compound. So those are our products of this double replacement reaction. Now, before we move on to the next example, and I will bring that right back, I do have one last thing that I want to add here. And someplace around this double replacement reaction area, please write down that charges don't change. Just in double replacement reactions, charges do not change. So what this means, and of course that wasn't as necessary to talk about with the first one because all of those elements and compound pieces always had the same set charges. But what you see in this second example is possibly lead. Pb is one of those transition metals that doesn't have the same charge every single time. And so that lead is going to be a little bit trickier to work with, but we're going to use this fact, the fact that charges don't change during a chemical reaction, to let us find the charge of the lead in the compound that it's starting in, and it's going to have the same charge in the compound that it ends up in. So let's go ahead and start working with that problem again, get this stuff back together. Okay, so we start by breaking our compounds into pieces, and those parentheses really help me visualize that special group so I don't even have to check the back of my periodic table. And the moving of my pieces is still going to start off the same way. I'm going to try and take the Pb and the I and put them together into my first product. But as I'm trying to check my charges, I has a -1 charge like it always does, but we don't know Pb's charge. So if you ever get into that situation, as long as it's a double replacement reaction, we're going to come back over to the original lead and this lead nitrate and figure out what lead's charge was here and use the same charge over on the product side. So remember that to find the charge of those transition metals, we have to start with whatever it's connected to. So nitrate's charge is a -1. And because I needed 2 nitrates, 2 -1s, to balance out whatever lead's charge was, lead has to be a +2. Remember that compound charges always add up to 0 for our ionic compounds. So -2, +2 cancel each other out. And that means that over here, lead is going to be a +2 charge still, which means that we are going to have to cross-drop reduce that over onto our I. So let's go ahead and get that 2 there and clean up these charges, because charges never end up in our formulas. They cancel each other out and disappear when these elements get together. All right. That's really the only special different thing going on here. We're still going to have to go take our other pieces and put them together, though. Potassium and nitrate getting together, K going first because it's the positive charge. But luckily here it's a +1, just like our sodium was up above. And because nitrate is still a -1, then that KNO3 is the final form that that formula needs to be in. So hopefully that's not too bad. We've practiced this skill a couple of times, and you're actually going to need that type of skill in order to be able to do the redox stuff that we're going to do if you haven't watched that podcast already. So it's a good idea to practice that a bit in order to get good at it. It's something we're going to need moving forward. So looking at these next two examples, we have another transition metal here, that Fe, but these pieces are a lot easier to break up. But as we start to look at that Fe and put it with our S, we have to know the charge of Fe to be able to balance it out with sulfur's -2 charge. Oops, sorry, I'm trying to put those together as if they didn't start off together. I need to highlight my elements so that I can keep my brain on straight. Fe is going to be trying to get with Cl, not with S. But it's starting off with S, so we can use S's -2 charge to help us figure out that Fe is a +2 charge, and it's still going to be a +2 charge over here. So along with chlorine's -1 charge, this is going to become FeCl2. And then our leftover H is going to be getting with our S. And since H is a +1 charge, when H and S get together with that -2 charge, this is going to become H2S. Now, I want you to try out this last one. Find those pieces, figure out where you're breaking up your compounds, then mix and match those pieces, making sure you start with a +1 in each of your new compounds. One positive, one negative. So always start with that positive. Put those together on the product side, and don't forget to check the charges to make those compounds nice, stable, and happy. All right, so now that we're done talking and learning about all these different ways to predict these reactions in isolation as groups, what I'm going to ask you to do is the same thing, just, kind of mixed up. On pages 11 through 14. So this is going to give you random combinations of elements and compounds. Your first step is going to be to identify what type of compound you've got. And then once you know what type of compound, what type of reaction you've got, so that you can follow the rules for that type of reaction and predicting those products. So don't be afraid once you figure out the type of reaction to flip back to the notes on that specific type to help you as you're starting to put these together. I am only asking you to do the evens on this, so don't be too scared from the fact that this is page 11 through 14. It's just that little last bit of page 11, and then, yes, 12, 13, and 14, but these problems are really spaced out because you're going to be doing a couple of different things with them. So it really is just 12 problems total. The evens out of numbers 1 through 24 on these pages. So 12 problems and probably fit on a single page if I'd put them a little bit closer together and, not had the extra ones there. You can feel free to do the odds, but I'm not going to grade you on those in general. And I was going to recommend that you leave those for your future self, maybe on the day of our review or the night before the test, so you can do a couple more practice problems and make sure you still got these skills in addition to the other stuff that we are learning and practicing. So just make sure to do the evens. And I was talking about finding the type of reaction first. Make sure you actually write it down. I know you have to think through it in order to be able to predict the products, but I want to physically see the words: double replacement, single replacement, combustion, synthesis, decomposition, either underneath or beside wherever you have written out that product and finished balancing the equations. So identify the type, of course, predict the products like we just learned, make sure to write NR if something doesn't react, and then also balance these reactions. I haven't been balancing them on the last couple of pages because I just wanted to focus on getting you through these notes and didn't want it to take extra long. But I do want you to keep practicing those balancing skills and keep that in mind as you're writing out, predicting those products. Now, there is this red highlighted note that is written in your packet, and I'd really recommend that you highlight that or emphasize that to your future self, because there are going to be some places where you're going to need to put some transition metals into some compounds, And like what we saw in our double replacement, if we need to make a new compound with a transition metal, we can just check whatever charge it had before the reaction. But in synthesis and single replacement reactions, if we make a new compound, like here, if our iron can replace copper, it's going to be making a compound with sulfate. Make sure to check your activity series to see if this is actually going to form a compound here. And when it does, if it does, then you're going to need to know iron's charge, and it didn't have a charge over here for us to use. So what I'm telling you with this little side note is in these types of situations, treat iron like it is a +3. Still go and figure out what is sulfate's charge so you can cross drop reduce and get these numbers here. But otherwise you wouldn't be able to make compounds like this. So on this page and any others in this sequence, 11 through 14, if you find yourself needing to make a new compound with a transition metal, then come back and check what charge they should have here.